and welcome to another video. For those of you who don't know me, because this is addressed more broadly to the two flat earthers in this video that I assume have no clue who I am. I'm Olaf. Hi, I'm a physicist and astronomer. I'm doing my masters in both currently, and I would like to briefly talk about this temperature thing that you brought up in the debate with Craig from Fight the Flat Earth and Ocean from Matters Now against Ross Perry from Real Offended and Dustin Nemo. That happened on Modern Day Debates, depending on when this video went out, rather recently. And this is one that I hear commonly from flat earthers, right? And it boils down to, well, the temperature in the thermosphere is like 3,500 Fahrenheit or 3,000 or something like that. How come the aluminum doesn't melt? How come the insert metal or composite here didn't break down due to the thermal stress? I will let the flat earthers actually explain their own point.
My turn.
My turn. All right, Ernie.
One second, Ozzy.
I'll take a question. I will.
I reserve my time.
You still got 20 seconds.
All right. The Space Shuttle Thermal Protection System is a max 3,000 Fahrenheit. The
you know it's going to be good research when you have 4 pictures stitched together in one. That's how scientists do it properly, like me. Just so you know.
Reinforced carbon melts at around 4,200 Celsius. So there's no way that this thing would have survived.
I'd really like to respond to this one point,
35,000
please.
Fahrenheit.
Okay, so let me respond.
And Craig tries to give an explanation here. I find the explanation to be okay, but I think he tried too little in terms of science and too kind of broadly.
On to this one point, please. Right, so Dustin, I quite often go to the gym, and after the gym, I go to a steam room, right? Now, my question to you is, how hot is steam?
I don't know the steam boiling point.
I find it funny that he doesn't know the boiling point of water. But by the way,
Well, what is right? Steam that is 100 degrees centigrade plus and not get scalded. The reason for that is there is not enough of the matter that is 100 degrees centigrade plus to transfer that heat energy to me.
And Craig in principle is correct here, although I wouldn't necessarily have explained it with matter and more with particles, but that boils down to the same thing. Pun intended.
Same thing applies for the equipment in space. It is up there. Yes, there is temperatures that are that high, but there is not anything to transfer that heat energy to do the thing that you are saying would need to do to melt it. Simple.
Incorrect.
No, Craig was about right here, and you have very little idea about what you're talking about, and heat in general, I could tell from the debate.
Aluminum is actually a very efficient medium of exchange of energy. And
it's not about aluminum, it's about how the heat gets to the aluminum. You understand that?
By the way, there's no water that will survive at 35,000 degrees Fahrenheit. Your ass is getting
didn't
cooked.
Respond to my question.
Do you know what?
It's like, oh, there's a temperature that's above the boiling point of water, and it has to all boil immediately. There's a critical lack of understanding of things like heat capacity. And I would like to explain that in a bit. Just keep on going, so we're absolutely sure that I'm not explaining something that they didn't say.
What happens if you? I know what happens if you wrap.
Hold on, you didn't actually respond.
100 is not 35,000.
Also, the debate was a bit of a mess.
100 is not 35,000.
And cook it. See what happens.
You completely missed the point. Okay, in space.
I thought that was a decent point, but it's just not 35,000.
Ross, hold on.
Ludicrous.
Ross, chill out. My point is that in space there is not the matter that is 35,000 degrees to transfer that heat energy. To have the heat energy transferred to you, it needs to have physical contact, right? Except for the radiation, which is a different thing.
No.
So for the 35,000, I'm still talking. For the 35,000 degrees temperature to be transferred, there needs to be a medium to transfer that heat energy. So the same way that I can survive in a steam room where the temperature of the medium is over 100 degrees centigrade, that can survive in space because the medium is so thin. The medium is so thin.
300 degrees
Again, you are missing the point. You are missing.
No
You are
sense.
missing
Right,
the
let's
point.
let him wrap up the last 10
You would
seconds.
boil in that kind of steam.
Last 10 seconds.
I love how they keep saying you were boiling that steam, you were boiling the steam. And now I have to explain what's going on here, and I think Craig has done a sub-ideal way of pointing it out. I would have asked if a single collision with a particle that was hot enough would suffice to melt something. But let's go back to my, and you all know what's coming now, OneNote's notebook, and explain the whole thing. Alright, here we are back again at my OneNote notebook, and I would like to talk about space and temperature. So first of all, what is temperature? Just so we all have the same understanding. Temperature is a property of particles, in this case molecules when we're talking about things like air and stuff. So it's most likely molecules like N2, O2, a bit of CO2, things like that. And the average velocity of a particle is linked to its temperature via this relation right here. So you have the average velocity of a particle is the square root of 8 times the Boltzmann's constant times its temperature divided by pi times the mass of the respective particle. So if a particle is hotter, then it will move faster. If a particle is cooler, then it will move slower. Please note that this is a distribution. It's called the Maxwell-Boltzmann distribution. I could go into great detail explaining it because I'm a big fan of it. But the most important part here is that not all, like say you have a room that's filled with a gas that has a certain temperature, not all of the molecules will be at the same velocity. Quite the contrary, some will move extremely fast compared to the average velocity, and some will move very slow. So it's really about statistics here, right? And I think this goes over the head quite a bit. So why do spacecraft not melt at 2,300 Kelvin, which is about the 3,500 Fahrenheit that I mentioned in one of their slides? It has to do with heat capacity and the number of particles, right? The number of particles because, again, the temperature is related to the velocity of a particle. So if more particles hit you, you have more heat transfer, right? What's heat capacity? It's the amount of energy necessary to increase the temperature by a certain amount. And this is really what's going on. You're not exchanging temperature, you're exchanging energy. And that's the big thing. That's the huge thing that they don't get. What do I mean by that? An example. You have one of the most classical formulae that you will be introduced at the very beginning when you take a thermodynamics course in university. We even talked about it in classical mechanics because it's a really nice way to calculate things quickly. Let's say we have 1 liter of water and we would like to heat it by 10 Kelvin. That's 10 degrees centigrade. We take this formula right here where we have on the left hand side we have the heat, and on the right hand side we have the mass times the heat capacity times the temperature. Now, the heat capacity is a number that just tells you this many mass takes this much energy to heat up by a certain amount of temperature. In the SI units that I like to use, we have 1 joule per kilogram, for example, and the heat capacity for water is around 4,200 joules per kilogram. So it takes 4 kilojoules to heat up 1 kilogram of water by 1 degree centigrade. And that is quite a lot because water has a very, very high heat capacity. Calculating that, so what would the energy be for 1 liter? By 10 Kelvin, we would get 42 kilojoules. That is quite a lot. That is really much. For comparison, maybe a bit of an odd comparison, a bullet that comes out of a rifle is around 1 kilojoule. So that's a lot of energy right there, right? This is with a density of 1 kilogram per liter, of course, because we have the mass here, and I said 1 liter, so obviously. Okay, so now what do I mean by all of that? Why am I explaining all of this? Because heat capacity is important. The aluminum has a certain heat capacity, and when one particle hits the aluminum that on its own would be hot enough to melt aluminum in principle, was all of the aluminum that hot, only transfers a tiny amount of energy, and this tiny amount of energy will not result in the aluminum melting. It will result in the whole aluminum thing heating up by a tiny amount. So what's really important is the density. Let's talk about the density. The density in the upper atmosphere at around 200 kilometers is 10 to the 13 particles, this is in particles, per cubic meter, right? At the surface normally we have 10 to the 27, so that's like a whole different story. And I would like you to just compare now. We have, just compare the temperature over the density. The temperature increases by a factor of about 10. Here on the ground we have 270 Kelvin. Up there we have, let's say, 2,000 something Kelvin, right? That's about a factor of 10, conservatively. And the density increases by decreases by a factor of 10 to the 14. So while yes, there is an increase in temperature, there is a significant decrease in particles that have that temperature, and thus a significant decrease in the amount of particles that can hit the spacecraft and melt it. And to show you just how bad it is, I would like to compare the internal energy of the gas. This comes from Joule's second law. The heat is the heat capacity times the number of particles times the Boltzmann constant times the temperature. And when you multiply all of these, you get the internal heat energy of a certain gas, ideal gas, of course, approximated. And when we put our things in here, per volume, per unit volume, let's say we give both of them the same volume, and we take a bit of gas from the surface and a bit of gas from the thermosphere, we can see by just putting those numbers into relation that the gas at the surface of the Earth is about 10 to the 13 times more energetic than the gas that it's up there. 10 to the 13 times. That's so much. That's I do apologize, that's 10 tera somethings, right? That's so much. And now, flat earthers, please try to follow me here. There isn't enough energy up there to melt the aluminum. The spacecraft would have to sit up there for many years, probably decades, right? Centuries even. It's so flustering when you bring that up, because it shows that you have no idea how temperature works, like none at all. The temperature up there is so high because there are extremely few particles there. Only the most energetic ones here on Earth can make it up there, and they stay up there. And it's like you as Craig said, when you swim in boiling water, you would die very quickly. But you can sit in a sauna with steam that is as hot as boiling water for hours. I wouldn't recommend you do that, but you could, you know what I mean? So, for flat earthers, and this is an important verdict here, there are a lot less particles that can collide to transfer energy up there. The energy density up there is actually 10 trillion times, that's trillion with a T, 10 trillion times less than what it is on the surface. So this is why it doesn't melt. The temperature alone cannot do it. It could be 1,000,000 degrees up there, and it would still not melt if it had the same density. There are too few particles to transfer energy. There is too little that can do things. Okay? It's really not difficult. Alright. With that, I think I will end this video here. I thank you so much for watching. If you enjoyed this video, please do consider leaving a like. And if you liked it a lot, maybe considering subscribing. And until the next video, I wish you a nice time. Goodbye!